Okay, guys, so this is going to be a very short video. We're just going to go over 4 slides quickly. 2, 3. Okay, anyway, 4 slides plus minus. So just a few examples here. This first one, I want to show you guys what to do when there's a division and you also need to substitute. So in this example here, the substitution is the first part, and then after that it becomes a usual problem where we convert division into multiplication and invert the second fraction. So here we have 4x divided by -6, where first we substitute. So x is given by -2/3. Division by -6 doesn't change. Now this is multiplication because of the bracket. So this can be rewritten as, if you prefer, 4. We could rewrite 4 as 4/1, if you prefer that. Multiplied by -2/3. And the divided by -6 does not change. Then, as we know, multiplication is simple with fractions. The top, we just multiply the two top numbers. The bottom, we multiply the bottom numbers. And the division, we leave that alone for a little bit. If you remember, according to BODMAS, whichever we come across first from multiplication and division, when looking at the expression left to right, we do that first. So looking at this expression left to right, we come across multiplication before division. Well, on the top and the bottom as well, because top and the bottom are separate things, right? That's part of the B in BODMAS, brackets, which also encompasses fraction bars. Okay, so anyway, simplify the top, we get -8 on top, the bottom we get 3, divided by -6, which we can write as -6/1, if that helps you to see this as a fraction. And then we invert the fraction, second fraction, that is the first one, we leave it alone. Invert the second one and change division to multiplication, so this becomes 1/6. Now, we can't simply cancel out the negatives at this point already, knowing that negative times negative is positive. So we can immediately drop it if you want to. I'm going to keep it to the end, just in case I confuse anybody. But note that at this point, you could drop both negatives. So this is -8 times 1 over 3 times -6. 3 times -6, is that right? Did we mess something up? Okay, I think we're okay. Okay, so this at the top is -8. At the bottom, we have -6, 12, 18. Right, now it's clear. We have a negative on top, negative at the bottom. So negative divided by negative is positive, just 8/18. Can we simplify that further? I think we can. If we divide both top and bottom by 2, we get 4 at the top, we get 9 at the bottom. Can I simplify further? I don't think so. Okay. So that's that example done. Now we look at integers. So to understand what an integer is, we need to do a quick recap. Okay, we first looked at natural numbers. If you guys remember, natural numbers are just the numbers which come to you naturally when you want to count anything. So for example, counting the number of computers on a table, you have to count 1, 2, 3, 4, and so on. Those are natural numbers. They come to you naturally when you try to count. And then whole numbers are just natural numbers with the inclusion of 0, right? The inclusion of 0. Okay. All right. And integers is basically just the positive and negative of whole numbers, right? If you see right here, that's all it is. It goes all the way to negative infinity and positive infinity. And we should note that integers don't include numbers like a half. A half would sit somewhere here. That's not included in integers. So do not include halves and fractions and things like that. Integers are just simply the numbers that you see here. Okay. Absolute value on the number line. So I think everyone knows what a number line is, but we use it here to define an absolute value. So if you haven't seen an absolute value before, it looks like this. I'll give you an example to define it. If we want the absolute value of 2, it's just a 2 in these two sort of like straight brackets. Okay, and that means the absolute value of 2. And the simplest way to understand an absolute value is that it always returns the positive version of a number. So 2 is already positive, so the answer to that is 2. If I take the absolute value of negative 2, the answer to that is also 2. So it always gives you the positive version of a number as the output. And the more technical way to think about it is that it gives you the distance from 0 to your number on a number line. So I'll draw a number line here quickly, 0, 1, 2, 3, minus 1, minus 2, minus 3. And the absolute value of 2 is represented by the distance from 0 to 2, right? We see we move 2 units to get there. And now we see why the absolute value of a negative number is still positive, because the absolute value of negative 2, according to this logic, is the distance we moved to get to negative 2, right? We moved 1, 2 units, right? We moved 2 units, 2 positive units. So it's sort of like thinking about a scalar quantity, not a vector. We don't consider direction, we just worried about magnitude. In terms of magnitude, we moved 2 units to the left, but still just 2 units. So that's why the absolute value of negative 2 is still 2. Okay, and a few examples at the bottom here. Find the absolute value of the following. 1, we know would just be 1. Negative 3 is just 3. Negative 4 is just 4. And 7 is just 7. Okay, straightforward. And this example here is similar. It's just a substitution problem. So absolute value of x when x is equal to negative 7 will just be absolute value negative 7, which is just 7. Okay. Now opposites. For some reason we need to know this. We define the opposite of a number as simply the negative of a number. So for example, if I take 3 and I ask you what is the opposite, you will tell me negative 3. Okay, simple as that. Adding integers with the same sign and adding integers with different signs are very simple sections to understand. In fact, you probably don't even need to look at these sections, but if you want to, you can have a quick browse through it. But it's a bit of an odd thing. I mean, if you are confused about how to add integers with the same sign and different sign, probably would have struggled to reach where we have already. So I don't know, I find the placement of these sections a bit odd. But anyway, if you do have troubles, but try not to take this because it's quite long, and I think it gives you strange ways to add and subtract things, which are a bit not very intuitive. But if you're in doubt, just ask me, okay? But I would recommend just rush through the sections very quickly. Don't take them too seriously. Okay. Rational numbers and real numbers. So rational number can be written as the ratio between two integers, right? So a rational number, I'll just write it here in a very strange kind of shortcut, but just to remember, a rational number is just the ratio of two integers. Z is the symbol for integers. So anything that can be written like this is a rational number. Okay, so examples here for us to look at. 0.5, is that a rational number? We will say yes, it is a rational number, even though it doesn't look like it is. 0.5 is technically half. So it can be written like this, 1 over 2. 1 is an integer, 2 is an integer, so 0.5 is rational because this is integer over integer. The number pi is irrational. Well, pi is given by 3.14. There's a point there, 3.1415, so on, whatever the digits are. And this cannot be written as integer over integer. So no, this one here is not rational. The first one is, second one is not. Third example is 2 3/4 rational. Well, you might say no because it doesn't look like it's only integer over integer, but this is a mixed fraction. It can be written as an improper fraction, and then it should satisfy the criteria. So let's have a look at that quickly. If you don't know how to convert a mixed fraction to an improper fraction, that's okay. Probably might have seen it a long time ago, so just look it up And if you don't want to look it up, I'll give you a very quick version right here of how to do it. So you take the 2 in front, multiply by the 4 at the bottom, and just add the 3 on top. And at the bottom, you just leave it as it is. 4 is there, so we just leave that alone. So at the top here, we will get 8 plus 3, 8, 9, 10, 11 over 4. 11 is an integer, 4 is an integer, so this is integer over integer. So it satisfies our definition of a rational number, and we are happy with that. That is rational. Example 4, is negative 0.25 rational? Yes, I would think it is. Now the negative sign might throw some people off, but remember negative 0.25 can be rewritten as negative 1/4. If you're not sure about these things, just check them in your calculators. Just put in 0.25 and you'll see it will convert it to 1 over 4 for you. Okay, now 1 over 4 with a negative in front is the same as negative 1 over positive 4, which is also the same as 1 over negative 4. It doesn't matter where you put the negative, but if I'm sure you can see that in either case, whether you're looking at this one right here or this one right here, it is an integer over an integer. So it is rational. Okay, by the same logic, in example 5, negative 10 over 1 is rational. And is 3 rational? Some people say no because it's not integer over integer. But technically 3 is the same as 3 over 1. You divide by 1, that doesn't change anything. So 3 over 1 is integer over integer, so it is rational. And by the same logic, example 7 is also rational. Again, you can move the negative sign from the 3 on top to the 1 at the bottom, wherever you like. It doesn't matter. It's still integer over integer. Okay. Comparing rational numbers. Okay, so this is something that hopefully most people are familiar with. Inequalities is just a way to compare numbers. So which number is bigger and which number is smaller. And here there's a very silly way to remember this. Let's see where we're getting to. Okay, so this is the last slide we need to do. So sometimes people forget which way the inequality needs to point. So I'll give you guys a very silly example with a picture. Suppose we had something like the number 7, and the number 7, let's say, is holding a spear. Let's try and draw a spear here. And the spear, big spear, the spear is, I don't know what number could be here, maybe the number 1. Okay, so the spear is stabbing the number 1, right? There's some blood maybe if you want, I don't know. Okay, so the point of this is that the big number is oppressing the small number. So the big number is spearing the small number. So the direction of the spear shows you which way the inequality sign needs to point. It points from the big number to the small number. Okay, it's a silly thing, but if it helps you remember it, then sure, use the method. If it's too violent for you, then don't worry about it. Okay, whatever works for you. Okay, and this is covered in the next lecture, so let me stop there. This was just an intermediate video because somehow in the lecture, these few slides were missed. So I was just recapping that. Okay, all right, that's it for this recording. Stop the recording, and the next video will catch up from where we left off here.